This tutorial is about the design and analysis of structures in the commonly used structural materials. We will start by looking at what we mean by these words, and then goes on to explain the process that designers perform in order to successfully evolve solutions to structural problems. Finally, two distinct approaches or design philosophies are explained: the traditional permissible stress method, and the more modern limit state method. An important point to make at the outset is that structural design is a highly creative activity, and not just a case of plugging numbers into formulae. It is also an activity which must be done responsibly, in order to produce safe structures. In mechanical engineering, most manufactured products with a structural component, like cars for example, can be repeatedly tested to destruction to prove the design at the prototype stage. Modifications can then be made before the product is put on the market. With most civil engineering and building structures, there is no prototype. The design must be right first time. These structures can also have a very long working life of 100 years or more, and it is the responsibility of the designer to ensure that the structure remains safe throughout its projected life. Structure. The word structure can be used to describe any organized system, such as the management structure of a company, or the structure of the atom. However, for the purposes of this tutorial, we will limit the definition to the following. A structure is a system for transferring loads from one place to another. In the case of building structures, this often means transferring the load of people, furniture, the wind, as well as the self-weight of the building itself safely down to the foundations and hence into the ground. The word analysis is generally taken to mean the process, whereby a particular structure, with known loads, is investigated, to determine the distribution of forces throughout the various members that make up that structure. Also, it includes determining the distribution of stresses within individual members, which result from the forces imposed on them. Finally, it covers the calculation of deflections. In other words, how far the structure will move under a particular set of loads. The analysis of a structure is necessary to prove that it is strong enough to support a given set of loads and that it is stiff enough to limit deformations. Analysis tends to be based on mathematics, and the aim is to get as close as possible to the uniquely correct solution. Analysis is a vital part of the design of safe and cost-effective structures. However, it cannot take place until the basic form of the structure has been decided. We firstly need to settle questions, like, should we use steel or concrete? How many supports to the beam should we provide? These early decisions are referred to as design, and not analysis. Design is a more difficult word to define than analysis because it means such different things to different people. The term designer is commonly used to describe people who design patterns on carpets, or determine the shape of motor car bodies. Engineering design or structural design is equally creative. Just consider the brilliance of the Forth Railway Bridge or the Golden Gate Suspension Bridge, two very different solutions to the similar problem of building a long-span bridge over water. Even within our own field, the word design can be used in two very different ways. Firstly, it is used to describe the whole creative process of finding a safe and efficient solution to an engineering problem. Consider, for example, the above case of designing a bridge across a river. There is of course no correct answer, but out of the infinite number of possible solutions, some are clearly much better than others. It is the job of the designer to come up with the best solution within available resources. The second way that we use the word design is in a more restricted sense. It refers to the activities, which often come after the analysis stage, when the forces in each structural member are known. It is the process of determining the actual size of a particular steel column or the number of reinforcing bars in a reinforced concrete beam. This is referred to as element design. Determining the number of bolts in a connection or the length of a weld is called detail design. There may be several choices open to the designer, but element design and detail design are not as creative as the broader design process. They are, however, very important, and bad detail design is a major cause of structural failures. The design process. The best way to explain the general approach adopted by a designer in solving an engineering problem, for example, the design of a child's garden swing. Clearly, with a small project like this, the formal procedure outlined here would not be consciously followed. The designer would simply use his or her judgment to determine the shape of the swing support structure, and the size of the members. Nevertheless, it illustrates the steps necessary for the successful completion of larger projects. The usual starting point for a project is a client who has a requirement, and the client will approach the designer, who is often a consulting engineer or architect, and commission him or her to produce a design which satisfies the requirement. The first thing that the designer will request from the client is a clear description of exactly what is wanted. This is called the design brief. In our case, the client is a child who requires a garden swing, and the brief is, provide, within a period of 2 weeks, a garden swing, which will be a play facility for many years. To arrive at a satisfactory solution, the designer will go through the following stages. Stage 1 is the site survey and investigation. Suitable locations will be examined and checked to ensure that there are no obstructions within the arc of the swing. Problems of access must be considered and the ground conditions in wet weather taken into account. Finally, a few trial holes might be dug to check that any rock is not too close to the surface to prevent foundations being excavated. Stage 2 involves investigating alternative structural concepts. There are an enormous range of structural shapes and materials which could be used. Each of these must be evaluated against clear rational criteria in order to select just one or two schemes for further detailed consideration. The type of factors that would be considered in relation to each scheme are as follows. Swing fixed to tree. This is the cheapest and best solution, but there is no convenient tree. A tubular steel frame. They are available from the supermarket. Little labor is involved and the swing is mobile. There are some concerns about cost, durability and appearance, but it is worth bearing in mind. Suspended from a helium balloon. An interesting solution, but totally impractical. Welded and bolted steel beams. Very robust, but it would have to be prefabricated by a local welder. The result is exceedingly ugly and would require painting to prevent rust. Timber frame with concrete foundations. Good appearance and relatively cheap, but high labor content and some maintenance required for good durability. Timber and steel bracket fixed to wall. Unless it is possible to fix the swing away from the corner of the wall, there will be safety problems. The choice therefore comes down to either a tubular steel frame, or timber frame with concrete foundations. We will assume that after due investigation of available products, the decision is made to go for the timber frame. Stage 3 involves more detailed development of the selected scheme. The basic overall dimensions must be decided. A method of bracing the frame to prevent side sway must be found. The type of timber to be used will probably be decided at this stage and the range of available sizes investigated. Stage 4 is the assessment of loads on the structure. This is not such a straightforward task as you might at first think. The following issues need to be settled. Should the swing be designed solely for the weight of a child? Or should it be assumed that at some time during its life an adult may use it? I would suggest the latter. We need to increase the load by a percentage to allow for the fact that the load is dynamic, in other words, the load is moving, and we must take account of the effects of its inertia. Also, the load may be suddenly applied if someone jumps onto the swing. Increasing the static load by, say, 100% ought to be enough to compensate for these effects. The load is not always applied vertically downwards. When the load is inclined, it causes much more severe bending and overturning problems for the structure. Wind loads often cause severe lateral loads, although they are not much of a problem with thin skeletal structures. Additional forces result from the actual self-weight of the structural members. With structures such as large bridges, these forces are usually much bigger than those that result from the traffic passing over the bridge. These self-weight loads present a problem at this stage of the design process because we do not yet know the final size, and hence weight, of the structural members. The designer must therefore make intelligent estimates which should be checked later. Obviously, with increased experience the designer gets better at making these estimates. In our case, the effect of self-weight will be very small and could be ignored. Stage 5 is the analysis of the structure. Firstly, we must transform the diagram of the proposed structure to obtain a simplified structural model which is amenable to analysis. This chiefly involves classifying the joints between the members as either pinned or continuous. The loads are now applied to the structural model and the frame analyzed to determine the forces and the amount of bending in each member. It may be necessary to carry out more than one analysis for different load cases. For the swing structure we would probably do it twice, firstly with the load vertical and secondly with the load inclined to produce the worst overturning effect. Stage 6 is element design and detail design. Each member must be considered in turn. Taking into account the forces obtained from the analysis, the required size of the member is calculated so that acceptable stresses are not exceeded. Careful thought must be given to the connections so that forces are adequately transmitted from one member to another. The designer must check all the possible ways in which the structure could fail. Finally, with real structures, the designer must clearly communicate his or her requirements to the builder by means of detailed drawings and specifications. It is not always possible to separate the process into such neat steps, and often analysis and element design will proceed in parallel. Also, the analysis to calculate the displacement of the structure can only take place after the member sizes are known. Design philosophies. The loads which will act on a structure throughout its life, and the strength of many structural materials, particularly those that involve naturally variable materials such as timber, masonry and concrete, are difficult to predict at the design stage, and we must accept that even the best of estimates may be in error. It follows that sensible design procedures must allow for these uncertainties by including factors of safety. A simple definition of a factor of safety is factor of safety equals load to cause failure divided by actual load on structure. Clearly the value of the factor of safety must be greater than 1 to prevent collapse. The magnitude of the factor of safety that we should aim for depends upon the predictability of both the loading and the material properties, but can range from about 1.5 for steel structures up to 5.5 for brickwork. The main difference between the two approaches that will be described is the way in which adequate factors of safety is achieved. Permissible stress design. Permissible stress design is the method formally advocated by the national standards for all materials. It has now largely been replaced by the following limit state approach. It is included here because it is still in widespread use by many designers and it remains the accepted approach for mechanical engineering components. In essence, the permissible stress codes of practice provide the designer with a maximum stress value that can be used for a particular material. This permissible stress is not the failure stress for the material, but is reduced to provide a factor of safety. As an example, designers are instructed to limit the stress in a mild steel beam to a permissible value of 165 Newton per square millimeter, whereas we know that it can actually withstand about 275 Newton per square millimeter before yielding. The designer must ensure that the permissible stress is not exceeded at any point in a structure. This process is intended to provide an adequate factor of safety to compensate for errors in both loading and material strength. The designer may, however, be unaware of the precise value of the factor of safety. Apart from collapse, there are other defects which can render a structure inadequate, such as floor beams which sag too much under load, or cracks in concrete which are too wide. These problems must be dealt with in addition to checking the stresses. The main criticism of this approach is the fact that the designer cannot vary the factor of safety to compensate for the degree of uncertainty concerning the loads. Limit state design. This is the approach is generally accepted throughout the world. The aim is to be clearer and more scientific about the aims of the design process. We have seen how a structure can be in such a state that it is unfit for use, in other words, excessive deflections or cracking. The point at which it is unacceptable is known as a limit state. The aim of the design process is therefore to ensure that a structure has an acceptable probability of not reaching a limit state throughout its life. This seems to be largely stating the obvious, although the use of the word probability is highly significant. It implies that we are aware that in the real world we must accept some failures from time to time. Clearly some limit states are more important than others, the most important obviously being collapse, and this is termed the ultimate limit state. All the others, such as excessive deflections, are termed serviceability limit states. The limit state approach allows us to set a higher probability against reaching the ultimate limit state than the other less important serviceability limit states. In practice, the principal way in which the limit state approach differs from the permissible stress approach is that the factors of safety are explicitly stated, and applied separately, firstly to the loads and secondly to the ultimate strength of the material. The difference between the two design philosophies is clearly illustrated in the following example. A corner of a warehouse building is supported on a short brickwork column. With a permanent load on the column. From weight of the building itself equals 600 kilonewtons. And a variable load equals 450 kilonewtons. The column is constructed from Class B engineering bricks with mortar made from 3 parts sand to 1 part cement. We need to determine the cross-sectional area of the column if the design based on 1. Permissible stress method. 2. Limit state method. Permissible stress method. The total load equals 600 plus 450 equals 1050 kilonewtons. Class B engineering bricks have a guaranteed minimum crushing strength of 50 Newton per square millimeter as individual bricks. However, when built into a brickwork wall, the mortar joints produce a considerable reduction in crushing strength. The permissible basic stress for brickwork made with Class B engineering bricks and 3:1 mortar is 3.3 Newton per square millimeter. This figure already contains a safety factor to take account of errors in estimating the loads, and also possible variations in material strength. As a result, area required equals 1050 times 1000 divided by 3.3, which is 318,200 square millimeters. Limit state method. The first stage is to apply load factors to the permanent and variable loads. Limit state design recognizes the fact that it is easier to predict the permanent load from the weight of the structure than the variable load from the building contents. Therefore, a safety factor of 1.35 is applied to the permanent load and a higher factor of 1.5 to the variable load. The factored load is called the design load. Therefore, design permanent load equals 1.35 times 600 equals 810 kilonewtons and design variable load equals 1.5 times 450 equals 675 kilonewtons. So the total design load equals 1485 kilonewtons. The strength given in a limit state code for a particular material is known as the characteristic strength. It does not contain a safety factor. We must therefore apply a safety factor to the material strength, which varies between 2.3 and 3 depending upon the degree of quality control used. We will assume that the highest standards of quality control are used for both the manufacture of the bricks and the site construction work, hence material factor equals 2.3. Assume the characteristic compressive strength equals 16.3 Newton per square millimeter. Therefore, design strength equals 16.3 divided by 2.3 equals 7.09 Newton per square millimeter. As result, area required is 1485 times 1000 divided by 7.09 equals 209,000 square millimeters. In comparison, the permissible stress method requires an area of column 52% greater. If we had not assumed special quality control in the limit state method and consequently increased the material factor to 3, then this difference reduces to only 16%. It is clear that the permissible stress approach is simpler and quicker than the limit state approach, but it does not provide as much scope for logically fitting the design to the prevailing conditions. Some designers argue that the permissible stress approach should have been retained for simple jobs. Summary of key points. Number 1. Structure can be defined as a system for transferring loads from one place to another. Number 2. Design is a widely used term that is applied to everything from, say, the creative conceptual design of a bridge to the detailed design of a bolted connection. Analysis is the mathematical part of the design process that is concerned with the determination of forces, stresses and deflections within a given structure. Number 3. In general, all structural design should comply with national or international standards and should only be carried out by competent and qualified designers. Number 4. Permissible or allowable stress design tries to ensure that at no time during the working life of a structure will the stresses exceed a safe value which is always less than the actual strength of the material. Number 5. Limit state design is based on probabilities. To guard against reaching the ultimate limit state of collapse, individual safety factors are applied to both the loads and the material strength. In other words, the material strength is divided by material factor. In addition, the structures should be checked against the serviceability limit state to ensure that they do not crack or deform too much. Thanks for watching. We hope you found some useful tips. Check out our website at structuralengineercalcs.com. Let us know what would you like to see next. The human footprint is a masterpiece of engineering and a work of art. Stay safe. Goodbye, and see you soon.